Because we know that in the aqueous state, that compounds in the aqueous state that are ionic do break apart into anions and cations, we like to show that in what's called ionic equations. So for example, what we're going to do is instead of, say, in a chemical equation, writing something like NaCl aqueous plus AgNO3 aqueous. Instead of writing them as aqueous, they're not really a compound together. So we do know in the aqueous sort of phase that this really exists more as Na plus and Cl minus. They're free floating around. And this isn't AgNO3 tied together. This is Ag plus and it's NO3 minus. So they're not really together. So we like to show that for soluble aqueous compounds by using what's called ionic equations. And we'll get to that in a few minutes with this net ionic equations. Okay, so the net ionic equation eliminates ions or compounds that are not directly involved in the reaction. Okay, so we're able to do that. So for example, if this sodium is floating around in solution here, and as a product, it's also floating around in solution, we're able to eliminate that. Okay, so there's a few steps in doing this. So step is we want to break up all of the electrolytes dissolved in water into ions. So electrolytes dissolved into water into ions. So that's similar to what I did up here. So our electrolytes, our strong electrolytes, are going to be anything in the aqueous phase. So our strong acids and our soluble ionic compounds are going to be our electrolytes that we can break apart. Okay, so again, what we're going to look for for this is the aqueous phase label. So if it has the aqueous phase label, we're going to be able to break it up into ions. We do not do that with solids, liquids, or gases. So I'm even going to say on this, just to kind of remind us, we don't do that with solids, gases, and liquids. Those aren't electrolytes, those are molecules. They don't break apart into ions or insoluble compounds. So when we say broken up, we're talking about the word, it means dissociated. Dissociate is exactly what we did up here. We took this, how we write it in a chemical equation, we dissociated it. We removed the anion and the cation and made them be independent, which is how they actually are in solution. Okay. So if you can name the compound and write the formula like we did in chapter 5, we should be able to determine the ions that make it up. So recognize common polyatomic ions and realize that most cations are monatomic. So I do want to sort of highlight this as well. Are polyatomic ions. So if it's one of those ones we talked about in chapter 5, you don't break them apart you don't break them all the way down into elements. You keep polyatomic ions as polyatomic ions. They're just polyatomic ions floating around in solution instead of, an atom. Okay, so let's start with this example here. We have 2 Na3PO4 aqueous plus 3 CuCl2 aqueous to give us Cu3PO42 solid plus 6 NaCl. Okay, so if we look, we're going to have to figure out all of our ions. Each of the 2 compounds of sodium phosphate will yield 3 sodium ions. So each one of these 2 is going to yield 3. So we're going to end up with 2 times 3 gives us, so for this one, 2 times 3 gives us 6 sodiums. Okay, and 2, if we look at the phosphate, this coefficient tells us we get 1 phosphate from each. So 2 times 1 gives us 2 phosphates. Okay, so if we go to our next compound, there's 3 copper chlorides. So we'll get, and if we kind of look, 3 coppers, and then we'll get 3 times 2, which gives us 6 chlorides when we dissociate here. Moving on to our next one, we have Cu3PO42. So we might want to say like 3 copper. Nope, we don't do that. So I'm going to put a box around this. Okay, this is not an electrolyte. This is a solid. So if you look back when we talked about evidence of chemical reactions and things like that, this would just be a solid floating at the bottom of your test tube. We keep this as is. We're not breaking this apart into ions. Okay, so our last one, we have 6 NaCl. So this is aqueous, so we can break this apart. We're going to get 6 of each ion. So when we do that, we have those coefficients down here. So what we have here, where we've taken everything that is ionic. So this was a strong electrolyte that was ionic, soluble ionic compound, soluble ionic compound, soluble ionic compound. We took all of these that are aqueous and showed all of the ions. We kept this as a solid because it's a solid, it's not ions floating in solution. So when we did all of this and showed the actual ions floating in solution, we did what's called the complete, or some call it the total ionic equation. Okay, so breaking everything apart and showing all of the ions, keeping our solids, liquids, and gases as solids, liquids, and gases, is giving us what's called the complete ionic equation. Okay, so on our way to getting to sort of what's going on in the reaction, we're going to, after we have that, we're going to do what's called identify spectator ions. We're looking for what are called spectator ions. So these are ions in solution that are present on, this is important, both sides of the equation. So these will be ions that are on both sides of the equation. So if we look back at our total ionic equation here, excuse me, a little too far. If we look at our total ionic equation, we're looking for ions that are on both sides of the equation that are unchanged. So I do want to kind of note for this, both sides of the equation. I want to sort of also say that they have to be in the same phase. Okay, so we're looking for things that are on the same side, and they do also have to be in the same phase. So if this, for example, was in a solid, and over here it's Na plus aqueous, that wouldn't work. They would have to be in the same phase as well. So they can't be both, say, solids, one solid, one liquid, or one aqueous and one solid, or something like that. Okay, so if we look at what we have above, so the only thing, if we look, we have 6 Na plus aqueous. These are exactly the same. So these are called spectators. So I'm going to cross them out. So one's on the left side of the arrow, one's on the right side of the arrow. If we look, phosphate is an ion here, but now it's a solid here. Copper is an ion here, but now it's incorporated into the solid here. So these are not going to cancel each other out. But if we look, we have 6Cl minus and 6Cl minus here, both aqueous. Those ones do cancel out. So our spectators are the 6 Na plus and the 6 Cl minus. They're on both sides of the equation. These are called spectators. Okay, so after we identify what spectators, we're going to remove the spectators from the equation. So we're just going to take them out. Like I sort of drew the line through them, we canceled them out. So once we remove spectators, we are left with the cation and the anion that came together in solution to form our insoluble product, our copper 2 phosphate. So this here is the net ionic equation. So our net ionic equation happens after we remove spectators. So the net ionic equation showed us what really happened in the reaction. We had copper ions. After we mixed the two together, the copper and the phosphate were drawn together like little magnets, and they produced an insoluble product, the copper 2 phosphate. So what happened in the reaction? All of the ions are in solution at the start. So once we mix the two together, The copper 2 and phosphate will form the insoluble product and what's called precipitate out of solution. So precipitate means we form a solid product. Because they form a solid, we do not break these compounds into ions. So they are not free-floating ions in solution. Sodium and chloride ions remain in solution and do not change during the course of the reaction. They were aqueous at the start, they were aqueous at the finish, so that's why they are eliminated. So this asks us to draw the reaction below. Okay, so before the reaction, we had, say, 2 containers. So in our first beaker, we'll call it, we have Na3PO4. Na3PO4. So we'll make the sodium, make it pink. So we have sodium ions in solution, and we'll make the phosphates, we'll make them blue. Okay, so I do want to, let's see, put a couple more in there. Okay, so we have ions in solution. Our second one, so in this beaker, we'll say it's a beaker. In this beaker, we have CuCl2. Okay, so we'll make the copper this sort of green color. And we'll make the chloride this orange color. Okay, so to start, ions in solution, so I drew them as little dots here. So they're in 2 separate containers. So when we initiate the reaction, we pour these 2 together. So this will be our products. So our products we know from our reaction are Cu3PO4 solid and NaClAq. Okay, so we'll draw this one bigger so we can really draw our ions out here. Okay, so when we mix these together, we're going to form a solid. So we're going to have our copper, which I made green, and we're going to have our phosphate, which I made blue. They're going to form a solid precipitate. So I'm kind of just going to draw it down here. That's the solid precipitate at the bottom. Okay, so not ions in solution. So this is a solid, and we call this the precipitate. Okay, so it's the insoluble. Okay, so it formed an insoluble product. It formed a solid at the bottom, so it drew the copper ions and it drew the phosphate ions out of solution to make the precipitate. Okay, so what was left is the sodium and the chlorides. Okay, so we have sodium ions still floating in solution, and we have the chlorides. And then we'll draw the top of this, sort of our water level at the top. Okay, so the sodium and chloride ions are left in solution, they're aqueous, and then our copper and our phosphate came together to form that insoluble product or that precipitate down there at the bottom. So we had the little pink dots, our sodium, still little pink dots over here, no change, that's why they're spectators. And our little orange dots that are little orange dots over here, again, no change from here to here. Those are spectators as well. Aqueous on one side, aqueous on the other. They became spectators. Okay, so let's do a couple practice problems here to show this net ionic, total ionic. Okay, so first we're going to go complete ionic, and then we're going to go into the net ionic. Okay, so what I like to do when I start is I identify what's going to be an electrolyte I'm going to break apart and what's not. So I'm going to break this apart. It's aqueous. That's aqueous. That's aqueous. This is not. And this is not either. So those ones I'm not going to break apart. Okay, so anything that's left, I'm breaking that apart into ions. So when I do this, this gives me 2H plus. This one here gives me 2Cl minus. That subscript 2 there tells me I have 2Na plus. And then I have my carbonate, which is CO3 2 minus. And so I have 2 hydrogens, 2 chlorides, 2 sodiums, and 1 carbonate. Okay, on the other side, this is also aqueous, so I'm going to get the 2Na plus, and I'm going to get the 2Cl minus. Okay, so I don't have a whole lot of room here, so I dropped the aqueous phase label, but all of these have aqueous phase label, which is going to be important when you put this in the computer for your homework. Okay, so I also have H2O liquid, and I have CO2 gas. So again, these are not electrolytes, these are molecules, so I kept them as is. Okay, so this would be my complete ionic right here. So for the next part, we're going to identify spectators. Okay, so looking, I see I have Na plus and Na plus. So that is a spectator there and there. If I look, I have Cl minus and Cl minus. Those are also spectators. So those are going to be removed. So now to get my net ionic, I'm going to have 2 H pluses, a CO3 2 minus. Those are going to come together and form H2O liquid and CO2 gas. Okay, so removing my spectators, I have the H ions and the carbonate coming together to form water and carbon dioxide gas. So this is my complete ionic, and this is my net ionic here. Okay, so next looks like we have aqueous, aqueous, solid, aqueous. Looks like here we're looking at a precipitation reaction again. So again, I'm going to go through and look. Aqueous, so that means it's soluble, it's ions in solution. Aqueous, same thing. This one's a solid, this is my precipitate, so I'm going to put the box around it. And this one is also aqueous, so I'm going to break that apart into ions. Okay, so my subscript 2 here tells me I have 2 Cr3 plus. Okay, so this is if you go through and look at your sulfate that has to have the -2 charge. This has a -2 charge to make this balance. This chromium has to be chromium 3 plus. Okay, so this 3 here tells me I have 3 sulfates. Okay, so here I have a coefficient and a subscript. I'm going to multiply those together. I have 3 times 2 gives me 6 ammonium. And this 3 is going to go with the carbonate as well. So I get 3 carbonates. Arrow, Cr2, CO3, 3 solid. Okay, and then last over here, looking at what we have, again, 3 times 2. I'm going to go down here, gives me 6 NH4 plus, and then 3 SO4 2 minus. Okay, so this is my complete ionic where I've taken my aqueous compounds and put them in here as ions, where my solid precipitate is still a solid precipitate there. Okay, so now I'm going to look for spectators. So chromium is an ion here. It's not here. Sulfate is an ion, and it's an ion here, so we can cross that out. Our 6 ammonium, same on each side. And our carbonate is now over here, so that one's good. Okay, so what I'm left with is my cation and my anion that come together in solution to form my precipitate. So 2Cr3 plus 3 CO3 2 minus arrow to give me the Cr2 CO3 3, and that's a solid. Okay, so this is my net ionic. Again, in a precipitation, it shows the anion and cation. So my cation and my anion that form the insoluble product. Okay, our last one here is a equation where it has magnesium, the element, displacing hydrogen in a compound. So this is a single displacement, or this is an oxidation reduction reaction. Okay, so I'm going to look. Magnesium here is a solid, so this would be like magnesium metal. And over on this side, I have H2 gas. So that is also going to be a compound that I'm not breaking apart into ions. So my two compounds here that I'm going to break apart are HBr and MgBr2, where this and this are going to stay the same. So Mg solid plus 2H plus 2Br minus arrow. Now we have Mg2 plus 2Br minus plus H2 gas. Okay, so let's take a look at what we have. Okay, so it's kind of tempting to say that this and this should cancel out, but they don't. So look here, magnesium is a solid. On this side, magnesium is aqueous. So they're not the same. So this is a hunk of metal. And my ring isn't made of magnesium, but that's pretty close to what magnesium looks like. Just a little more flimsy. So this is magnesium solid. For example, magnesium in this way is an ion in solution. Like, for example, we have magnesium in our drinking water. Doesn't look anything like this. Okay, this is an ion in solution. So these are not the same thing. So again, I said that to cross them out, they have to be in the same phase. This one's solid. This one is aqueous. So we're going to leave those alone. Our hydrogen is aqueous here, and it's a gas here, so it doesn't cancel. The only thing that's exactly the same on each side is the bromide ions. So those are the only two things that cancel. So if we look at what we have left, we have Mg solid plus 2H plus give us Mg2 plus H2 gas. So it's kind of important to note in single displacement reactions or in redox reactions, what's left in your net ionic equation is your species that are oxidized and reduced. So if we look, what we have here, magnesium is going from neutral because it's an element to having a +2 charge. So here it has a charge of 0. It's a neutral element. And now it has a charge of +2. So magnesium has lost electrons, which means it was oxidized. And so if we look at the other element present, that's our hydrogen. So hydrogen goes from +1 to elemental hydrogen, which is neutral. To go from positive charge to neutral, you have to have gained electron, which means it was reduced. So in a single displacement, we should only end up with our elements that were oxidized and reduced in our net ionic equation. So again, magnesium oxidized from Mg solid to Mg2 plus, and hydrogen reduced 2 H pluses to giving us H2 gas.